In this lecture, we will discuss some more numericals related to the magnetic circuits. So let us start with the example number one. In this, the statement of the question is that there is a rectangular iron core which is shown in the figure one, and this is the figure one, and there the mean length of this magnetic path is 100 centimeter, and the cross section is 2 by 2 centimeters square. The relative permeability of the iron is 1400, and there is an air gap which is 5 mm, and it is shown here. So the air gap, the uh, length of this air gap is 5 mm, right? So there are three coils basically which are connected, which are wound over this iron core in such a way that uh, the magnetomotive force of two coils is in the same direction and one coil is in the opposite direction. So let us say that there are an a number of turns of this particular coil. There are, let us say, n c number of coils of this coil, and there are n b number of coils turns of this particular coil. So n is the number of turns, nc is the number of turns, and nb is the number of turns. Now the current in this coil is, let us say, 1.6 ampere. The current in this coil is 4 ampere, and the current in this coil is 3 ampere. And the direction of the current is also shown. Now we have to find out the flux in the air gap. To find out the flux in air gap, we will, let us try to find out the solution of this particular question. Now, because we have to find out the flux, the total flux, not the total flux, basically, we have to find out the flux in the air gap, right? Now, in this question, we are not given any leakage of the flux. So, we will assume that flux leakage and fringing is zero. That means there is no leakage of the flux, there is no fringing. So this means that whatever flux is associated with this iron path, the same flux is associated with the air gap also, right? So the flux in the air gap is same as that is available in the iron path, right? Now, so that means if we can calculate the flux associated with the iron path, we can easily calculate the flux in the air gap. So the total flux in iron path is equal to total mmf divided by the reluctance, right? Or you can say total reluctance. So that means in this particular circuit, the magnetic circuit, we have the total reluctance. If we can find out the total reluctance of the circuit, we can easily find out, and we can find, if we can find out the total mmf of the circuit, we can easily find out the total flux of the iron path, and the flux in the iron path is the same as that means the flux in air gap is equal to the flux in iron path, right? So let us try to find out what will be the total mmf here. Now, since there are three mmf sources here, so this is, let us say, the source A, and this is, let us say, source C, and this is, let us say, source B. So there are three sources. So we can say that FA is nothing but it is equal to IA and A, and FB is equal to IB and B, and FC is equal to IC and C, right? So if we calculate this one, this would be 1.6 into, and then NA is 335 here, right? Similarly, IB is 4 ampere, and the number of turns is 600. And similarly, NC, IC is 3 ampere, and number of turns is again 600, right? So now this is equal to, now we can easily calculate this one. So on calculating this one, so this is 536 ampere turns, this is 2400 ampere turns, and this is 1800 ampere turns. Now these three mmf, so the total mmf is the, algebraic sum of these three magnetomotive forces, right? Now let us find out their direction also. So in this particular case, in the coil number A, uh, if we have to find out the direction of the flux, so we need to curl our fingers into the direction of the current, and the thumb will give us the direction of flux. So the flux is here, so the flux is flowing like this. So this is the direction of flux, right? Similarly, if we curl our finger with the current, so the thumb will give us the direction of flux, right? Not this one, sorry. If you curl it, so thumb will give us direction of flux, so which will be downward. So if you curl your right hand fingers, right? So this is your right hand, okay? So the fingers curl and thumb will give you the downward direction. So this is in this way. So now here you can see the current is going from behind of this coil. Okay, so it is behind. So if you curl your finger, like your hand is this is so we can draw the fingers here. Okay, so if you curl your finger, so your thumb will give you the direction. So direction is here like this. Okay, so that means the direction of FA and FB is clockwise, right? But the direction of FC is anti-clockwise. So we can write FA plus FB minus FC. So by adding all these, we have got, so if you add them, 536 plus 2400 minus 1800, so the total flux is 1136 ampere turns. So this is the total flux. Now we need to find out the total reluctance of the circuit. This is, let us say, 1. Now we will find out the total reluctance. The total reluctance, we know that reluctance is the property of magnetic circuit by which it opposes the flow of flux through it. The total reluctance of the given magnetic circuit is, So let us say it is S, so it is equal to the reluctance associated with the iron path plus reluctance associated with the air gap. So where Si is the reluctance of the iron path and Sg is the reluctance of the air gap, right? So the general formula of S is it is equal to L upon mu naught into mu R into A. So this is the general formula, standard formula of the reluctance. So Si is equal to Li divided by mu naught mu R and A, where Sg is the length of the air gap divided by mu naught into A. Now here mu R is equal to 1 in this case. In case of air gap, mu R is 1, right? So now we can substitute the values here. So we can see the values Li. So the mean length of magnetic path is 100 centimeter and the area of cross section is 2 by 2 centimeters square. The air gap is 5 mm, right? So total length of, so let us try to solve, mean length of the circuit is, let us say, L, which is equal to 100 centimeter, right? So this is uh, now the length of air gap is 5 mm, right? So this is, let us say, Lg. So Li means the length of iron path will be L minus Lg. So this is 100 into 10 raised to the power minus 2 meter minus 5 into 10 raised to the power minus 3 meter. In meter it is. So Li is equal to 100 into 10 raised to the power minus 2 minus 0.5 into 10 raised to the power minus 2, and this is in meter, right? So this would be equal to, so we can write it as 100 minus 0.5 into 10 raised to the power minus 2 meter. So this would be 99.5 into 10 raised to the power minus 2 meter. So this is the length of the iron path, right? So we can find out now area of cross section. If you see, the area of cross section is this one, which is 4 centimeters square. So this is A. So area of cross section of the air gap and the iron path is same here, right? So A is 4 centimeter square. So this will be equal to 4 into 10 raised to the power minus 4 meter square. So this is the value of A. So we can find out the value of Si. So it is equal to Li divided by mu naught mu R and A. So this would be equal to 99.5 into 10 raised to the power minus 2 divided by 4 pi into 10 raised to the power minus 7 into mu R is given as 1400. So it is 1400 into 4 into 10 raised to the power minus 4. So on calculating this value, we have got Si is equal to, the reluctance of iron path is equal to, this would be 1.414 into 10 raised to the power 6 ampere turns per Weber, right? So this is, let us say, 2. So similarly, we can find out the reluctance of the air gap. So Sg will be equal to length of the air gap divided by mu naught, the permeability of air or free space, and A. So length of air gap is 5 mm. So this is 5 into 10 raised to the power minus 3 meter divided by 4 pi into 10 raised to the power minus 7 into A is 4 into 10 raised to the power minus 4 meter square. So on solving this one, the value is equal to 9.946 into 10 raised to the power 6 ampere turn per Weber. So this is, let us say, equation number 3. So the total flux in this case will be S is equal to Si plus Sg. So this will be equal to, so the total flux here is, if you add both, sorry, the total reluctance, it is not total flux. The total reluctance is the reluctance of iron path and reluctance of the air gap. So it, on adding these two values, um, 1.414 into 10 raised to the power 6 plus 9.946 into 10 raised to the power 6. So this will be equal to 11.36 into 10 raised to the power 6 ampere turn per Weber. This is, let us say, 4. Now we have the equation 1 in which we have the total flux here. Then we have the total reluctance also. So the total flux in fact is equal to, let us say it is 5, which is equal to uh, the total mmf divided by the total reluctance. Total mmf is equal to 113680, and total flux is 11.36 into 10 raised to the power 6, right? So on solving this, we can have the answer which is equal to 100 into 10 raised to the power minus 6 Weber. So that means the answer to this question is phi is equal to 100 micro Weber. So this means that because there is no flux leakage here, there is no fringing effect given, so we can assume these as 0. So the flux in the air gap is phi is equal to 100 micro Weber. So this is the answer to this particular question. Now let us come to the next example of today's class. In this, the statement is very simple. There is an iron ring which has the mean length of 1.2 meter and its cross section area is 0.005 meters square. So this is square in fact, and it is wound with a coil of 900 turns. So if the current of 2 ampere is flowing in the coil and it produces the flux density of 1.1 Tesla, so we have to find out these four parameters: the MMF, magnetomotive force, the total flux in the ring, magnetic field strength, and relative permeability of the iron at this flux density. So that means this is a ring. This is a ring which has, it does not have any air gap, right? So the area of cross section of this particular ring is given. So the A is 0.005 meter square, and this ring also has some turns. So let us say turns are like this, and there is some current I is flowing here which is equal to 2 ampere, and the number of turns of this is 900, and the mean length is 1.2 meters. So the given parameters are, solution will find, so given parameters are mean length L, which is 1.2 meter, the area of cross section, which is 0.005 meter square, and N is also given, which is 900. Then the current in the coil is 2 ampere, and flux density B is 1.1 Tesla, right? So the first is magnetomotive force we have to find out, M M F. This we have to find out. So how will we find out this one? It is very simple. So the formula for this is number of turns into the current in the coil. So this is N into I. So N is 900 here and I is 2 ampere. So we have 1800 ampere turns. So this is the total MMF of this particular ring. Then the second thing we have to calculate is the total flux in the ring. So as we know, the flux density is equal to the flux phi and the area, right? So from here we can find out flux, which is equal to B into A, and B is given to us, which is 1.1 Tesla, so it is 1.1, and A is also given, which is 0.005 meter square. So the value of flux density in this case will be equal to 5.5 milli Weber, right? So this much of flux will be produced in the iron ring. Then the third parameter is we have to calculate the magnetic field strength. Now the third thing is H, we have to calculate the magnetizing force. So H is basically equal to the magnetomotive force divided by the length, the mean length of the magnetic circuit. So we can write it as F upon L, and F is nothing but it is N into I divided by L. So F we have already calculated here, which is 1800, right? So this is 1800, and the mean length is given to us, which is 1.2, right, meter. So the value of H is equal to, if we solve this, we have 1500 ampere per meter, or 80 per meter, right? Whatever. So this is the answer for this particular part of the questions, the part C, or third part basically. So this is the C part, right? So this is the answer. Then we have the last part D. We have to find out the relative permeability of the iron at this, right? So at this flux density, right? So how will we find out the relative permeability of iron? Now, as we know that the magnetic flux density and the magnetic field intensity H are associated to one another by this formula. B is equal to mu H, and we also know that mu is nothing, it is equal to mu naught into mu R, right? Where mu naught is the permeability of free space, okay? It is related to air or free space, and it is equal to 4 pi into 10 raised to the power minus 7 Henry per meter, right? So and mu r is nothing but this is the relative permeability, right? So we can find out the value of you know uh, relative permeability. So we can write B is equal to mu naught into mu r into H. So we know B, which is also given to us. H we have calculated here, right? B is given, right? Mu naught is this one, and so we can find out mu r. We can rearrange this one. So mu r is equal to B divided by mu naught into H. So this will be equal to 1.1 Tesla is given. Mu naught is 4 pi into 10 raised to the power minus 7, and H we have calculated here, which is 1500. So mu r is nothing but it is equal to 583. So this is the answer. So we have calculated all the four required parameters here, right? We have calculated the total magnetomotive force, the total flux, and the magnetic field intensity or magnetizing force as given uh, here, right? And then the relative permeability also we have calculated. So in this way we can solve such numericals, and it is very easy and simple to solve the numericals related to the magnetic circuits. So this is all about today's class, and thank you so much.